Have you ever really thought about what happens the split second a bullet leaves the barrel? You might picture a straight line, but that's not it at all. It's actually this intense, unseen battle against the laws of physics. Today, we're going to pull back the curtain on that journey and demystify the science of external ballistics. And this quote from Hornady Manufacturing, one of the biggest names in the business, really nails down our focus. We're not getting into what happens inside the gun barrel, and we're not talking about what happens at impact. Nope. Our entire focus today is on that wild ride the bullet takes through the air, the world of exterior ballistics.
Hitting a target from way out there, way out there, has almost nothing to do with luck. It's all applied physics. It means you have to understand every single tiny variable that can push or pull on that projectile while it's in motion. It is literally the science of accuracy.
So, every time a trigger is pulled, this battle begins, and the bullet is fighting against these invisible forces from the moment it starts its journey. So, what are they? Okay, first up, let's talk about the bullet's basic flight path. What's the fundamental shape of its journey through the air? So the second that bullet leaves the barrel, its path stops being a straight line. Instantly, it immediately starts to follow this predictable arc, kind of like a long, graceful throw. And that arc is shaped by two incredibly powerful and constant forces. And here are our two main combatants, gravity and air resistance. Gravity is relentless. It's always there, constantly pulling the bullet back down to earth. And then you've got air resistance, or drag. Think of it like an invisible wall of wind that the bullet has to punch through, and it's always stealing its speed. Now, gravity is pretty simple to figure out, right? But how do we measure and deal with that invisible enemy? The air itself. How do we crack that code? Well, the key is this value called the ballistic coefficient, or just BC for short. Basically, it's a single number that tells you how good a bullet is at slicing through the air. The higher the BC, the more aerodynamic it is, the better it beats that air resistance. But hold on, because BC isn't some magic number, and there are a lot of myths about it. For one, it's not a fixed number. It can actually change depending on the altitude, the temperature, the air pressure, and it's just a measure of efficiency, not some stamp of goodness. A higher BC doesn't automatically mean a bullet is better for every situation. Okay, now this is where it all clicks. Check out this table. We've got two bullets, both the same weight, both fired at the same starting speed. But look at the difference. The Spire Point has a much higher BC, and at 500 yards, it's still moving way faster and has dropped almost 20 inches less than the round-nosed bullet. Wow, that's the power of aerodynamics right there. All right, so we've got a handle on air resistance, but what happens when the battlefield itself isn't flat? How does shooting uphill or downhill totally warp the equation? So let me ask you this. You're aiming up a pretty steep hill. Common sense would tell you that gravity has more time to pull on the bullet, right? So it should hit low. Makes sense, doesn't it? Well, get ready for this because the answer is completely counterintuitive. Whether you shoot uphill or downhill, the bullet always hits higher than it would on flat ground. So the big question is, why? It all comes down to the fact that gravity only pulls straight down. When you shoot at an angle, less of gravity's force is actually working against the bullet's forward path. So the only distance that gravity really cares about is the horizontal distance to the target. Shooters call this the true ballistic distance. You always have to aim for that horizontal distance, not the actual line of sight distance. Okay, so if you thought that was getting complicated, buckle up. Because when we start talking about extreme long-range shooting, you have to account for more than just gravity and air. Now the planet itself starts to fight back. First up, you've got the Coriolis effect. It's a trip. Because the Earth is literally spinning underneath the bullet as it flies, the bullet seems to drift to the side. And here in the Northern Hemisphere, that drift is always to the right. It's a tiny, tiny effect, but over 1,000 yards or more, it can be the difference between a hit and a miss. And then there's the Oathus effect. This one's even more subtle. If you shoot east, you're shooting with the Earth's rotation. So the bullet gets a tiny little boost and hits a bit high. Shoot west, against the rotation, and it hits a bit low. We're talking about incredibly small forces here, the kind that only matter at the absolute limits of performance. And as if that's not enough, don't forget the Earth isn't flat. Over a 2,000-meter shot, the ground itself will have curved away by over 31 centimeters. That's about a foot. You are literally shooting over the curve of the Earth. How wild is that? So let's take a breath. We've got gravity, drag, weird angles, and even the spin of the Earth.
But all these physical laws don't mean a thing without the most important part of the equation, the human element, the person who has to calculate all of it. I mean, think about it. That is a massive amount of data to process for a single shot. With all these things fighting against the bullet, how is it even possible to be accurate at all? And this really brings us to the core human challenge. The physics, well, that's predictable. But for a lot of people, the ability to even engage with these concepts is blocked by something way more personal, a fear of the math itself. It's a real thing. It's called mathematics phobia. And this isn't about being bad at math. As the research shows, it's an intense, real fear that can actually interfere with your brain's ability to function logically when you're looking at numbers and problems. And this fear doesn't just pop up out of nowhere. A lot of the time, it's rooted in our past experiences. Maybe a school system that was all about passing exams, or a classroom where you felt afraid to ask questions. All that pressure from society to just be good at math. It builds up, and it can create a real wall between us and learning something fascinating, like ballistics. So that's the final thought I want to leave you with. The physics of a bullet's flight, as complex as it is totally knowable. It's not magic. And maybe the real unseen battle isn't against gravity or drag at all. Maybe it's against our own anxieties. So what great challenge could you take on? What could you master if you could just conquer the fear of calculating it?